Dear all, I will give a talk about the cosmic ray stability of medicinal formulations and fortified designer beverage nutrition for astronauts. In short words, I will talk about space food and space medicines. My name is Volker Hessel, and I'm professor at the School of Chemical Engineering and Advanced Materials at the University of Adelaide, and I'm the research director of the Andy Thomas Center for Space Resources. I'd like to introduce what kind of research we are doing in my group. This is shown on the next slide. We published 1 year ago this perspective review about the continuous flow extraction of adjacent metals in order to propose an economic operation to get resources from asteroids. We consider continuous flow, and I think the image shows that, as a disruptive technologies. So our approach is, first of all, technology disruption, and I've already cited the Angewandte Chemie paper here. Now, this vision which we gave in this perspective review, we have turned into reality by doing minerals processing with microfluidic technology on 2 asteroids, and this is published in the Journal of Separation Technology. Then we did go 1 step further, and we published the formation of nanodots in space in reaction engineering and chemistry. And the 4th manuscript, which is given, is an overview about the use of microfluidic technology as disruptive technology on the International Space Station, given in the journal Frontier Space Technology and in the section of microgravity. The second part of my research is about creating space resources in a circular way. So on the issue of systems engineering and circularity, we have published in Chemical Engineering Science. And just recently, we have published on the space farming, on growing plants in space, and how to positively use the stressors in space in the journal Science of the Total Environment. I like to start with space food systems. My main ambition here is to show how you can make a personalized food in space, which is better suited for the health of astronauts. I will then show space medicines, and here my topic will be the stability of those medicines. So on the first part, it's on the personalized manufacture of space food. Now, current space food is actually not very personalized. If you have a look here, there are dehydrated food items and there are thermostabilized food items. That doesn't look really like the menu list of a really good restaurant where you go in the evening for dinner. And I'm aware that people are working very hard to make better space food. And there are a lot of promises, but still I would say we are far from having the perfect nutrition for astronauts, because they are in a field of stressors, so they need an even better nutrition possibly than given on Earth. So how can we do that? So our vision is to have key nutrition components mixed with key medicinal components. And imagine here something like vitamin D or omega acids, and mix that together to a manufacturing unit in space, which can produce on demand and on site, meaning on the International Space Station or more generally in the spacecraft, the personalized drink. So we're working on a process concept for multi-product manufacturing with a library of functional beverages recipes. And that also includes the flavor, which is not shown here. Now, together with Beer-Tree Automation, which is a Dutch company, we work on such a systems concept. And here I show you such systems, which are the most advanced systems on Earth. The first one is a Pepsi Spire system. It is the vision of PepsiCo to make in this automat the company's whole range of beverages. And you are also supposed to do even new mixtures, which PepsiCo has not brought on the market before, so your personalized drink, or to add flavor. A similar product is a SodaStream Professional, which is meant for workplaces and universities. That is a novel water dispenser, and it allows to create an individualized level of carbonation, temperature, flavor, and intensity. Finally, I like to show you this Colibri product. Look at the brown color on top of it. That is some syrup given. And by shaking the bottle with the syrup, and dependent on the time, you can adjust the sweetness level to your individual favorite. So we have an innovative packaging which allows the personalized drink. And this product goes directly to the final consumers, while the other products are more meant for a bar or for a restaurant. Now we want to do in a way the same thing. And we want to use a microfluidic setup as an innovative tool as compared to the conventional tool, which is a burette. The microfluidic setup is a T-type of mixer, which creates some droplets, as we will see in a second. The color denotes blue is oil, and the gray stream, that is an aqueous solution. Now, we form droplets in both cases, but the mechanism is different. In the burette, we form it by gravity. Obviously, we cannot use that in space. In the microfluidic setup, we form by shear forces the droplets. And notably, everything is dominated by capillary forces. So in the microfluidic setup, we have microgravity conditions on Earth and in space. And that's why many people think microfluidic setups are perfect to operate in space. They show no or hardly any gravity effect. But let us go on. What happens now with those blue droplets formed? First of all, I like to say there are surfactants in the oil phase. Now, when the oil phase touches the water phase, an initial droplet is formed, and the droplet is around several hundred micrometers wide, so very large. But we want to make nano emulsions. The nano emulsions are formed by a kind of self-organization, which happens by the surfactant going to the interface, as you see in this picture, and the interface then becomes folded, and the surfactant crosses even over to the aqueous phase. In this way, it creates an instability, and very small nanodroplets are formed in the order of 100 nanometers. These are called cloud emulsions, which you know from many lemonades which you drink. It gives us, it is synonymous, this kind of mild opaqueness is synonymous with a natural appearance of those drinks. So finally, we get the nanodroplets, which are surrounded by the surfactants. We use Twin 80 as a food compatible surfactant, medium chain triglycerides as a food grade ingredient, and phosphate buffer. I will not talk in detail which ingredients our library contains to make the astronaut healthy. This will be the topic of a different talk. I will go only on key results for this emulsification process. Now, this is shown here. On the left side is drawn the average diameter of the droplets, and then we have the surfactant to oil ratio from 0 to 2, which is a key parameter to steer the droplet side. Now let us look what happens if we give the surfactant Twin 80 into the aqueous solution. What we then get are droplets which are 100 micrometers wide or a bit larger. So a normal emulsion and not a nano emulsion as desired. Obviously, we have to do it different. Now we put the surfactant Twin 80 in the organic phase, in the oil phase, and then we get the desired nano droplets around 100 nanometer and the highest surfactant to oil ratio. So we get a nano emulsion. if we want to see the performance of those two different emulsions plotted as size distribution, we see that the nano emulsion is a relatively sharp peak. It's almost symmetrical and it's monomodal. That's usually what you like. The normal emulsion with 100 micrometers average diameter is bimodal. So it has two maxima. I hope you can see the small maxima on the left side. This is not preferred as it's some kind of dispersivity which can be troublesome for the function of those emulsions. Further, the emulsion is a bit broader in the size distribution, so it is less defined. And anyhow, we want to go for the nano emulsion, but we have now found a way of doing so. We have found the way by a beverage. Now let's look what can and that is how the emulsion looks like. It has this kind of mild opaqueness, and therefore it's called a cloud emulsion. Now let us look when we use our innovative technology, our disruptive technology, which is the microfluidic one. We see here, it looks like we can make even smaller droplets at a given surfactant to oil ratio, but there's an even more striking advantage of using microfluidics. And this is what I want to show on the right side now. If we compare this to experiments at a surfactant to oil ratio of 1, you see that the burette needs around 25 minutes to do a certain emulsification job. The tea mixer is many times faster. Now this is important. When I stand in front of an espresso machine, I expect that I get the product immediately. I may want to wait 1 minute for the final espresso coming out, but I certainly will not wait 25 minutes. It's important to have a fast technique which forms the product in its final state in a fast way. That is essential for a personalized technique, and the microfluidics are here much better than the conventional technique. Now finally, we want to go with those emulsions in space. So first of all, let us form them in space. And we do this on a random positioning machine here from Airbus Industries, which is the golden standard in microgravity. And in this way, we can form emulsions under microgravity conditions. And what we then can observe is that we see smart differences between microgravity experiment and gravity experiment, which need further investigation. And we can make the same parametric experiments as we have seen before here. And you see the droplet sizes are also around 100 nanometers. It also looks like it depends a bit on the time, how we make it. As said, these are very first experiments. I don't want to go too far with the interpretation. And once we have those strings, and I remove now this window to here, we test in an artificial intestine, which is an organ on a ship at UniSA here in Adelaide with Professor Ian Johnson. We check the food uptake in cells under microgravity, meaning we do the same experiments as you see below on this RBM machine. And what we actually measure is a lipid uptake. And all the white spots which you see there are lipids. In this way, we can think about how an astronaut under space conditions might digest food. Now I come to the next topic. We want to make a space medicine formulation. A formulation is a drug embedded in excipients. And we have chosen tablets because tablets are so common. Tablets, excipients are solid, and they're around 10 or 8 to 12 solids, which are typically mixed together. We need so many different excipients because we want different function which one excipient cannot fulfill. We want a gliding behavior when we machine the tablet. We need a filler to make the tablet as large as it is, otherwise it would be so small we could not handle it. We need disintegrants, so in the stomach the tablet can dissolve colors and flavors, sweetness, and so on. So we need all those functions. Now, our ambition was, let's take them all from the moon. Maybe that is possible. There are a lot of inorganic resources on moon, and I'd like to show that on the next slide. Now, that idea attracted media attention, and already 2 years ago, we were in the Advertiser, which is Adelaide's newspaper, mixing moon dust pills for star trackers, and this was done together with Space Tango. And I will show you later that this resulted in a real NASA-ISS experiment. But let's look, what do we have on moon? You might know that there are quite some organic compounds in the tablet excipients, like cellulose or hemicellulose. This is not existent on moon, but we have inorganic materials, and we use inorganic materials for excipient, such as silica. And when Neil Armstrong put his footsteps on the moon for the first time, there was a lot of titanium dioxide. So we have all those materials available in the same or similar way than on Earth. And they are distributed over the moon, over the Mariana Highlands. And the Apollo mission has given us some samples, but recent satellite missions give a much better resource map of the moon than the first Apollo missions could give. So the message is, meanwhile, we know pretty well where the materials are. And in principle, we could start the mining on moon in this way. Now, coming back to our experiment, we have the excipients, and this is a list from the dibasic calcium phosphate until the iron oxide. Anything there in between is an inorganic excipient, and we think this material or a similar material is found on moon. Then we have ibuprofen as active pharmaceutical ingredient, the drug, and vitamin C in a similar function. In this talk, I focus alone on the ibuprofen, and we have also encapsulated flavor, just to mention. Now we made 60 tablets inside ISF, which were measured exposed to cosmic rays in a long duration stability study. And in another study, we have 6 tablets outside ISS. Now, what we could do is vary the supposed cosmic ray sensitive compounds. That's what we did. So they have different drug contents, for example. We vary the excipient mix as a whole. Sometimes we have a lot of iron oxide in the tablets, sometimes hardly any iron oxide. And you will see the reason soon. And we vary the supposed key excipients for cosmic ray stability. And iron oxide is one of them. And naturally, we need a small check on repeatability. We cannot make each tablet different. We need to check our results. All this experiments were kindly facilitated by Space Tango company, who made a lot of launches to ISS, and I like to give the name of Jana Staudemeyer from Space Tango, who made that all possible. Let us look what kind of radiation protection concepts we had. We are just here at the beginning, and I'm not aware that there are many radiation protection concepts proposed in literature. So that is the first step. The very obvious one is that we hope that the absorbing matrix, a solid matrix, which is not penetrable to all space radiation, is good on its own. So we just hope the Earth's medicines are good on its own. This is the absorbing matrix environment concept. So just the dilution of the API in shielding excipients will do the job. Now, on the opposite side, we might have specific molecular interactions. This is shown on the right side between ibuprofen and an excipient, such as an iron oxide. And then in the middle, we use something which we know from Earth. We have a lot of coating for controlled drug release. In space, the coating may have a different function. It may absorb the cosmic ray, rays. So we have a coating layer to protect the ingredients. Now, for some given reasons, and I don't have the time here to justify that, we think that those concepts shield pretty well against alpha radiation, especially the coating concept. There should be also some shielding against beta radiation, and against the coating concept is supposed to be best one. We don't think that the absorbing matrix environment concept and the absorbing coating concept is really good for gamma radiation. And finally, we think both concepts do pretty well against UV irradiation. The molecular interaction is a great unknown concept, and we need more investigations here. Now, why did we choose ibuprofen? First of all, there are a lot of ISS studies with ibuprofen, so data are in space available. And then it's very well studied on Earth, so probably there's no other drug decomposition better studied than that of ibuprofen. And here you see a photocatalytic study. So we know some or maybe all of the decomposition products. So we have pretty much knowledge where we can benchmark our space experiment too. Now, we have an ISS experiment, and I will report on that, but such experiments are still costly, and there's not easy access to it in the way we would like to have. We would like to have months-long access. So what we have to do is, on Earth, we have to simulate space radiation conditions. And luckily, we have in Adelaide great experiment to great machines to produce alpha, beta, and gamma rays. So we can study under what is supposed to be identical cosmic radiation conditions. Here you see the result with pure ibuprofen. So this is just ibuprofen powder, no tablet. Now, what you can see on the left side is a reference. That's pure ibuprofen. And on the right side, you see alpha irradiated. Obviously, there is a small peak above the other peak. So there's something new. And by the way, I should mention this is thin layer chromatography, a very easy but powerful technique for first analysis. Now, if we compare that with some decomposition product, which we know, we see that the spot belongs likely to 4-isobutyl-acetophenone, and we can exclude that it belongs to 4-acetyl-benzoic acid. So we have already, with a simple technique, a first idea what might happen under space conditions. I'd like to show you, before I like to show you the equipment, I should mention that the 4-isobutyl-acetophenone is neurotoxic, 10 times higher toxicity than ibuprofen. So definitely we have to prevent this kind of decay mechanism. Now I'd like to show you the equipments which we have, the core equipment. This is a particle irradiator. It's a radioactive isotope here, americium-214, and that emits alpha particles. We make an experiment again with pure ibuprofen, and we use UHPLC as separation technology. So this is ultra high pressure liquid chromatography. And it gives us the same information as we've seen before, but not visibly now with a peak. And here you see that we actually have, under different conditions, as I've shown before, quite a number of peak of decomposition products, and probably the small ones we would not see in TLC. So naturally, there are better techniques around than what we did with the initial investigation. I should mention that we can do the experiment under defined conditions. Gray GI here is the dose parameter, which is typically taken. We know those dose parameter, and this is given here as a function of the beam. I do not have the time to go into details why this is for alpha radiation alike. Now let's look on beta radiation. Again, we use a radioactive nucleate, strontium-90, to produce irradiation. We go again for pure ibuprofen powder, and we see that now, as a function of time, the ibuprofen decrease is quite considerably. So about half of the ibuprofen, or maybe even a little bit more, is lost in 5 hours duration. We match with the 5 hours around half a year at ISS. So basically, we use a higher intensity and we have a shorter time for a given reason, but we assume this experiment is representative for what is seen on ISS. And again, we have here the dose given in gray now per hour. We cannot easily make gamma ray experiment, but X-ray is the best, what is closest to the gamma rays. And the Royal Adelaide Hospital was so kind to help us with their equipment. And here we look now on ibuprofen tablets, so not on ibuprofen powder anymore. So we assume that should be better shielded, but not to gamma rays or X-rays. Look on the right side here. Here you see the reduction, so the loss of ibuprofen, and you see it starts with 4%, and the highest value is 21%. So what we learn is this is substantial. We learn also that this dilution matrix concept of Earth medicines will not shield against gamma rays. So we need space-specific tablets, at least in this case. And we learn that it's very much depending on the excipient mix which we have. So this dilution concept and also the specific molecular interaction of excipient and drug seems to have quite some effect, but still we hardly get to zero. Only one case where we have zero. So generally we have to live with that gamma ray destruction, and we have to do something against it. Now with that knowledge on Earth, we did go to space. This is the first Australia-led ISS NASA experiment, and you see the website here. And you see that it is on long-term stability of pharmaceutical ingredients for potential future in-orbit manufacturing. So we have here given the vision of making the tablet from moon materials. Now we followed an inspiration from Care One company, which has this red ibuprofen tablets. They're red because they contain an iron oxide core. And that is what we have seen before as one of the shielding concepts. And we made specimens which at least optically look similar to these commercial tablets. We packed the tablets into blisters. That is how you typically get your tablets when you open your pharmaceutical product. It's a package. The ground control sample is marked red, the flight sample is marked blue, and they have the same history. They took the same airplane to Houston, the same airplane back. So we did our best to make it comparable. Now, if you look at one blister, that's what you see on the lower left side, you see there are 20 tablets inside. Since we have 60 tablets, it is 3 blisters, and all tablets have a laser welding in between, so they are separated from the next tablet. I have mentioned just shortly, but I mentioned that we have also external ISS samples. So samples really outside in the outer space. The room there is very much limited, so we could only take a 6 centimeters times 6 centimeters blister with 6 tablets instead of 60 tablets. Now, space research is fascinating. When I saw a launch with our tablets, it was a very special moment. And again, I say thanks to Space Tango. I say also thanks to the launch provider, which is Northrop Grumman. And you see the mission patch given here, which we made for our experiment. You see the name of University of Adelaide. And this mission is NG for Northrop Grumman 14. It was launched not from the Kennedy Space Center, but from Wallops Island, Virginia, which is a bit higher, not so far from Washington. And that is an island where rockets are launched, and the launch was made at night. Now we had a second launch, and I have to mention here for the first time Alpha Space Company from Houston, who brought our tablets outside. Now it's NG-15, Northrop Grumman, again the supplier. And it was also launched from Wallops Island at day at the 20th of February 2021. So those tablets are still in space. But luckily, we received the first set of tablets which were launched last October and which came down this October. So they have 1 year space radiation history. Now let's see at the very end of my talk what came out. you may remember that we have this iron oxide and we use it as a coating. So we thought the iron as a heavyweight atom might shield alpha rays and hopefully might shield against other kind of rays. We made not a sample with 0% iron oxide for some reasons, but we made 1% as the lowest amount. We still call this practically no iron oxide coating. So imagine something like this here with a very thin, maybe porous coating around the excipient matrix which defines the tablet. Now, what do we see when we look at thin layer chromatography again? We see there's still some ibuprofen in the ISS samples. The ISS sample is on the left side, the right peak set. And we compare it again with pure ibuprofen, which is on the same TLC plate, but on the left side. What you directly see here and what is striking is there's a big decomposition product at the starting lines. This didn't move with the solvents we choose. So we know a little bit about the chemical nature, and I would guess that this is an acid compound. As ibuprofen is an acid, but a stronger acid, because obviously it did not move. We will make further investigations on the nature of this decomposition product. Now, when we compare it with ground control samples and a fresh sample, you see ground control and fresh looks the same. So obviously there was no decomposition for the ground control sample, and naturally not for the fresh sample. So it looks like, and I'm very cautiously here because we need to repeat and we need to make more investigation. It looks like we see here a space effect in terms of decomposition of ibuprofen. Now, our big hope was that a big coating with a lot of iron oxide will make a stronger case. So we put 25% of the mass of the tablet into iron oxide. That's around the maximum we could do. So this we call space radiation protection concept. And excuse me, you are the first people who see those results. The headline is wrong given as I see just here. So this is, yes, it is an iron oxide coating. So it's a wrong headline. Now, what we see with the big coating is we see just ibuprofen peak. We don't see any decomposition product as in last case. So again, very cautiously, we could say, yes, our stabilization methods work. There is a difference, which excipients you use, how you provide them. That might be a solution to make space medicines stable. By the way, there is a reason from the chromatography side that the ibuprofen sometimes looks a little bit different, sometimes as a more sharp peak and sometimes as a more vague peak, but I do not want to comment here on this difference. Naturally, in a paper, we will report why that is the case. Now I come to my last slide. I think I've shown, and I don't need to convince you all, you are all great space researchers, that space research is something which is important for the future of mankind, and therefore has a lot of web and media attention. We were lucky to have an ISS NASA experiment, and that has caused quite some attention. It put us into the position to make a book, which will be soon launched, where we are editors. There's my name given, but also Jana Staudemeyer and two other colleagues, a book on in-space manufacturing resources. I could take a position at Frontiers Journal in Space Technologies with a new section on space exploration. As I mentioned, a lot of newspaper, TV, and web releases. You see the number here. Probably it's more likely like 80 web releases which were made about space within just 1.5 years. And here you see some of them also given in German, so it's a global action. And the Spanish ones, they come partly from Argentina. So there's a lot of interest in all corners in the world, at every continent, virtually. And finally, I'm not sure if I ever will see the Mars landing. That might be still a while ago, but space is for the next generation. And here you see the first student in South Australia who was so lucky to get the space training program of the Premier, an industrial program. And we were so lucky to host this first space student at our site. So the point is, space is an ever young technology. It's for the new generation. Thank you so much for listening to me. Thank you all for organizing this great conference. Bye-bye.